Hello everyone. So today we are going to study about pulley block system. In this example, we have the pulley and the string which are massless, and the acceleration is given upwards, that is A, and we have a block of mass capital M. Now, so as to solve these kind of questions, we need to ask the block 3 questions. The 3 questions ask. The first question will be, where are you going? We have the same figure here and we need to draw the FBD of the block. Let us have mass M here, right? We are going to draw FBD. The block says it's going up as it is given the acceleration is A here. The second question comes into play, that is, why are you going? The block says, I think something is pulling me. What is the pulling force here? The pulling force is nothing but tension in the string. And the third question is, are you facing any problem? The block says, yes, I'm definitely facing a problem as my own weight gives me the problem. Now, according to Newton's second law of motion, we can form the equation as T minus mg is equal to ma. I have done T minus mg is equal to ma, and this will give the acceleration as positive because the block moves upwards in the direction of T. Now, let us solve a question. We have a question like this. Find the acceleration of system, and we are given g is equal to 10 meter per second square. The pulley and string are massless. So as to solve these kind of questions, it is very easy to solve using pulling force method. Pulling force method. Let us consider m is greater than m. So generally our idea states that it will move downwards for m, capital M, and upwards for small m. Now, using pulling force method, we have acceleration as net pulling force by total mass. So what is the net pulling force here? Well, we have capital mg for the heavier block downwards, and we have small mg for the lighter block downwards. What we will do is, net pulling force can be given by capital mg minus small mg, as we have a system moving like this, right? So small mg opposes the motion of capital mg, so it needs to be subtracted, and the total mass is given by capital M plus small m. So what do we have from this equation is the acceleration is equal to capital M minus small m into g by capital M plus small m. This is the most easiest method I find to solve these kind of problems. Now let us have another example. Let us take this question. The question states, find tension in the string and acceleration of the system. The wedge that is given here is at rest, and pulley and the string are massless. Now what we will do is, we will do the same process what we did earlier. We will give forces and distribute them. Like we have 5g acting downwards for the 5 kg block. G here stands for the gravitational force. And we have tension acting upwards. So if we draw the FBD of the 5 kg block, so we have 5g downwards and the tension acting upwards, right? So tension in the string will be given as what? 5g, that is equals to 50 Newton. this is what we can do. Now for the 10 kg block, what do we see here is it's 10g acting downwards and we have 30 degree here. So let us resolve the 10g into components. Along this side we have 10 sine 30 and along this side we have 10 cos 30, as this is 30 degree again. What is the driving force here? The driving force here is given by, for 10 kg block, driving force is equal to 10 g sine 30, right? And what's g here? Then we get it as 50 Newton again. So it's 50 Newton here, 50 Newton here, right? The tension in the string is 50 Newton because tension is an internal force in the string, and the tension here will be equal to the tension here, and we must note that the tension acts away from the block, right? Now we need to find acceleration. Using pulling force method, we can do it very easily. Acceleration is given by the pulling force method. So what are the pulling forces here? We have 10g sine 30 minus 5g by 10 plus 5. What I did here is known net pulling force by total mass. Now this net pulling force gives us the result as 0. So the acceleration of this system is equal to 0 meter per second square. That's all I'd like to state today. Thank you.